Hello everybody, my name is Pablo Merino. I am a PhD student at Universidad Politécnica de Madrid, and together with my supervisors, Professors Fabricio Macià and Antonio Souto, we have developed this work which title is On the Convergence of the Solution to the Integral SPH Advection Diffusion Equation with Rotating Transport Velocity Field. So, the schedule of my presentation is the following. I will first talk about motivation. Then I will present the problem and the setting. After that, I will deepen into the issue of transforming the equation to the Fourier space. Then I will present the results of convergence, show a numerical experiment, and finally, I will close this talk with conclusions and future work. Regarding motivation, well, convergence is a relevant topic in any numerical method. Concerning SPH, there are interesting works, mainly that by Franz and Wendland, and also those by Ben Musa and Villa. But in any case, there are very few studies focusing on diffusive operators. Along that line, however, there is the interesting research by Violot and collaborators, where the Laplacian operator is studied at the discrete level. Also, in the past SPHERIC edition, my supervisors and myself presented a work in which the convergence of the heat equation was studied. The purpose of this research is to extend the work presented therein, and particularly deepen into the study of diffusive operators in SPH using Fourier analysis. Now let me present the problem and the setting. First, let's place ourselves in the context in which the interparticle distance is much smaller than the smoothing length. This ensures that we are accurately approaching the SPH approximation at its integral level. The SPH kernel is defined as usual, where h is the smoothing length, and the function w is considered to be integrable, differentiable, attaining its maximum at x equals 0 and of compact support. An important fact is that the kernel is a radial function. This, in addition, implies that the Fourier transform of the kernel is also a radial function. So we introduce the function little w, the radial profile of the kernel's Fourier transform. We will often refer the derivative of the kernel by using the function f, which is common in the SPH literature. Now, the SPH operators are given by these expressions below. Notice that the approximation we are using for the gradient is the common one, and for the Laplacian, we will use this expression corresponding to the approximation to the Laplacian given by Morris and collaborators. In our past research, we introduced the function f. The function f is simply the first momentum of the kernel's Fourier transform and can also be expressed using the function phi, more convenient in order to express the Fourier representation of the Morris Laplacian. This expression was presented by ourselves in our last work, and you can see that the function phi appears here, containing the information of the symbol of the Morris Laplacian, as opposed to the symbol of the exact Laplacian, which naturally also appears. Now the equation we aim to solve is the following. Notice that we have both a transport and a diffusion terms. We place ourselves in the two-dimensional plane, and we introduced an initial condition. The advection velocity is given by the field v, which simply represents a rigid rotation, where the characteristic parameter is the angular velocity omega. From this velocity field, we can define a field of trajectories, which is simply a mapping of the plan into the plan, parameterized by the time. You will see that this function turns out to play an important role in our developments. Now, the SPH version of the previous equation is given by the following expression, where the exact operators have simply been substituted by their SPH expressions. Now, the aim is to apply Fourier transform to these equations and solve it in the Fourier space. The Fourier transform is given by this expression here, and conversely, we can also define the inverse Fourier transform. Now, we have already presented the Fourier representation of the Laplacian operator, so we are fine, but we need now to compute the Fourier representation of the advection operator. This point is a little tricky, so let's go for it. Let us define the operator L, which can be used in order to express both the exact and the SPH advection operators. So now I claim that the Fourier transform of the SPH advection operator is given by this expression here on the right. Don't believe me? Okay, let's check it. To obtain this expression, I have used two facts. First, the fact that the operator L and the Fourier transforms commute. This implies that the Fourier transforms of L applied to V equals L applied to the Fourier transform of B. And second, that for any radial function V, I have that L of B equals 0. See that after this first statement, I can translate the expression on the left to this here, where I have simply take the operator L out of the Fourier transform. Now I have the Fourier transform of a convolution. This is an easy one because, as you know, the Fourier transform of a convolution gives the product of the Fourier transforms. And also, when I apply L to a product of functions, say u times b, I get u times L of b plus v times L of u. Now, note that v here represents the Fourier transform of the kernel, and as it is a radial function, then this simply gives omega times the Fourier transform of the kernel times L applied to the Fourier transform of u, exactly what I have claimed at the beginning. Well, so with all these ingredients, we can finally write the Fourier version of our original SPH advection diffusion equation. This leads us to the following expression, where obviously we have the advection and the diffusion operators represented. The solution of this equation can be computed explicitly, leading to the following expression. And now, based on the properties that we have deduced so far regarding the operator L, we can deduce one extra property, which is the fact that the two operators, the advection operator that we can call AH and the diffusion operator that we can call VH, commute. This implies in particular that the exponential of the sum of the operators equals the product of the exponentials, and those can be switched. This important property allows us to rewrite the solution to the Fourier version of the SPH equation in this form here, in which, as you can see, the advection is represented not as an operator acting over u hat, but rather using the function that defines the trajectories by changing the point at which u0 hat is evaluated. This is a crucial point, as it simplifies the computations in the proof of convergence. Okay, so now let's go for the proof of the convergence. To do so, we will base ourselves in the well-known result, consistency plus stability equal convergence. So we define the error as the difference in the Fourier space of the SPH and the exact solutions. Now, this function, the error, solves the following equation, which, as you can see, has the form of the exact advection diffusion equation in the Fourier space, and where little fh is the following function. Now, applying Duhamel's theorem, we can find an explicit expression for the error given by this integral here. Now we repeat the trick, see that we have the advection operator here, and as it commutes with the diffusive operator, we can rewrite this expression by evaluating the function u hat h at a point affected by the rotation. And now, from this equation, taking into account the different properties that we have deduced so far regarding the advection operators, and also the properties that we have already presented in previous works regarding the diffusion operators, in particular that corresponding to the Morris Laplacian, imposing also the requirement that the function phi appearing in the Fourier representation of the Morris Laplacian is a positive function. As a side note, this is true for all the kernels considered in the numerical experiment. Then we can establish the following bound for the error in terms of its integral. This bound, and details are given in the text, finally lead us to establish the convergence in terms of the L2 norm. Well, let me then now present the numerical experiment. So we have set a grid of particles, as this that you can see in the figure top left, in which the particles are distributed in a disk which radius is large enough to ensure that we can consider this discrete problem as a good approximation of the analytical problem acting over the whole space. Then we set the initial condition that you can see in the figure top right, which is simply a Gaussian profile, and we leave it evolve until it completes a whole rotation around the origin. The parameters governing the diffusion and advection phenomena has been tuned so that the characteristic time of the diffusion phenomena, which is defined as the time in which the maximum of the initial datum is halved, coincides with the characteristic time of the advection, defined as the time in which the particles complete a whole rotation. This given, these plots correspond to time equals 0, time equals 0.5 the characteristic time, and the last one corresponds to the simulation time equals the characteristic time. Summing up, the discrete problem has been solved using a typical SPH discretization. Also, the integration in time has been performed by using a semi-implicit Hoying scheme. The error has been measured using a discrete version of the L2 norm and also the maximum norm. You can see in the plots below how for the different kernels tested, the linear and cubic splines, and the three well-known Wendland kernels, the convergence is achieved when h, the smoothing length, tends to 0, exactly as predicted by the theory. As a conclusion, the convergence of the advection diffusion equation with rotating transport velocity field has been established. This implies a step forward from previous results of convergence, and namely that of the heat equation. And also numerical experiments have been conducted showing good agreement with theoretical results. Regarding future work, well, an analytical approach to the convergence at the discrete level is considered as a natural continuation of this work, and also the aim of us is to apply this approach to more complex equations, namely the Burgers equations. We consider this as a good beachhead towards a more interesting study of the Navier-Stokes equations. Thank you very much for your attention.